मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, dear students, this is 32nd lecture in the series of mechanics of metal forming. As you know, we have covered so far the modeling techniques, starting from slip line, upper bound method, lower bound method, and all those things. In this lecture, we are going to discuss the finite element method, one of a very recent technique, especially numerical method. It is a numerical method for solving metal forming problems, all kind of metal forming problems. So, in this lecture, we would discuss the basic concept first, because once the basic concept is clear, one can make use of this for solving different problems. As far as the activities in metal forming, the limit analysis method, the force equilibrium equation, etc. Secondly, activity that could be method, that is the finite element method or finite element analysis. So, if you look at this figure number 1, this lists different formulation for simulation methods for simulating metal forming processes, including the formulation part and the physical, that is the physics part. So, where the modeling of the material, one can use the wax as the laboratory material for modeling metal forming problems, and then one can also use scale down models as which is shown in this figure. These all four are used in simulating the metal forming processes. So, let us start with the numerical method, which is finite element method out of these. And before going into the details of metal finite element method, history of finite element method, why it was felt to use FEM, because the all other methods earlier discussed, the slab method, slip line method, and even the upper bound method did not work well when we come across a very situation forming problems either of extrusion or forging or rolling or wire drying or some other processes, coining and all those things. So, the brief history is that the finite element method was first used by Clough in 1960, and that was also for plane elasticity problems. While solving the plane elasticity problem, Clough used the name which is called as finite element method in 1960 in very first beginning. But the idea of finite element method date back much further. The applied mathematicians, the physicists and the engineers each developed the essential ideas of finite element method independently at different times and for different reasons of their applications. The applied mathematicians were concerned with boundary value problem of continuum mechanics, in particular where they wanted to find approximate upper and lower bound for eigenvalues, whereas the physicists were also interested in solving continuum problems, but they sought the problem, the means to obtain piecewise approximation function to represent their continuous functions. Aerospace engineers, on the other hand, were searching for a way to find the stiffness influence coefficient of cell type complex structures. So, because of these reasons, different people, that is how the FEM has evolved from the mathematician side, from physician side and from engineer side. That is how the finite element method has evolved. In fact, finite element method, it's a process, it's a simulation process, simulation technique one can say. It's a numerical analysis also, or you can say as a technique for obtaining approximate solution to a wide variety of engineering problems, including metal forming. So, it is popular in academic institution and in industry because of its diversity and flexibility as an analysis tool. A finite element model of a problem gives a piecewise approximation to the governing equations. We would see what is governing equation later. The basic premise of the finite element method is that a solution region can be analytically approximated by replacing it with an assemblage of discrete elements. So, that we call as the nodes and elements. So, these nodes and elements are discrete in nature. So, in fact, the term simulation is derived from the Latin word which is called as simulare. Simulare, that means to pretend. However, the technical meaning of the simulation is the description and reproduction of physical and technical processes by use of mathematical and physical models. In comparison with practical tests, the simulation is often very cheap and not so dangerous. And if you look if you combine, so the combined with modern methods of computation, as now you have better computer, the simulation is a powerful tool which gains more and more importance for describing and developing new processing methods. So, and also because of higher requirement of the quality of products and narrow tolerances, when you look for the accuracy, better products. So, because of these and the narrow tolerances of measures, optimizing, planning and simulating of forming processes becomes more and more important. As the computational power has increased, you all you know, because of the very high speed computers at low cost. During the last years, which is now available easily, numerical method plays an outstanding role. The most important numerical method is the method of finite element method. Therefore, numerous finite element programs have been developed so far, which are able to solve linear, non-linear, static, dynamic, elastic, plastic, elastoplastic, steady state, transient problems, isothermal problems, as well as non-isothermal problems. During the last several years, these all has developed solution for all these varieties of problems. In this case, we have to differ between general purpose and special purpose program, therefore, because the variety of problems. Also, today many farming processes are carried out without a previous or accompanied finite element analysis, of course. However, if the material flow of the load of the rolling devices, for an example, have to be investigated exactly, the numerical simulation is a must if one does not want to invest too much money and time in practical experiments. Furthermore, practical experiments cause a loss of production of a rolling plant. For an example, if the material flow and the stresses in the rolling pieces as well as the forming tools are well known, so the critical forming steps and deformations can be corrected and avoided. That means, in manufacturing, temperature, distribution of tool and fluid mechanics are very applicable, and there are applications of these. So, FEM approach therefore begins with the governing equations of the problem and proceeds, and it proceeds without relying on variational statement. Using this method, the finite element method can be extended to problems where no functional is available, and it is widely used in heat transfer today, very acceptable way. If you see from the problem to model way, for modeling from on one side there is a problem and then how one can model the things. In fact, a given technical problem must be expressed by physical terms so that it can be formulated mathematically. What means modeling? That means if you can represent the physical term mathematically, that is what is the meaning of modeling. The model should therefore reflect the reality as exactly as possible in a natural way. However, it should also be as simple as possible. Furthermore, the model must be described this way that it can be implemented in computer easily. This is also very important. So, numerical problems like divisions by extremely low number or poor convergence of the iterations, like we would come across during the other lectures in subsequent order. If poor convergence of the iterations we come across, one have to be mastered, or to be this kind of situation has to be avoided. In fact, trial runs of the computational simulations and a subsequent check of the results by comparison with variety of physical experiments are therefore very important, and rather it is a must. A special attention has to be directed in fact to the boundary and initial conditions during modeling, therefore, because they have a decisive influence on the extent of the model as well as on the reliability of the solution. If the results do not coincide, if the result obtained by the finite element method, that is modeling, do not coincide with the reality or with the expectation close to reality, the model must be checked and possibly it needs modification, whereby it will become bigger and more complicated. So, with this basic very basic concept, let us see how finite element method works. Finite element method, where a continuum is defined as a body of matter, that is a solid or liquid or gas it could be, or simply a region of space in which a particular phenomenon is occurring. In a continuum problem of any dimension, either it is 1D, 2D or 3D, the field variable, whether it is pressure, temperature, displacement, stress or some other quantity, possesses infinitely many values, because it is a function of each generic point in the body or solution space, and therefore the problem is one with a finite number of unknowns. The finite element discretization, that we call as discretization or dividing into nodes and elements procedures, reduces the problem to one of a finite number of unknowns. Therefore, this is done by dividing the solution region into elements and by expressing the unknown field variables in terms of assumed approximating functions within each element. The approximating functions, sometimes called as the interpolation functions, are defined in terms of the values of the field variables at specified points that may be called as nodes or nodal points. So, nodes usually lie on the elements boundaries where adjacent elements are connected. So, this node it is connected with this element. In addition to boundary nodes, elements may also have a few interior nodes. The nodal values of the field variables and the interpolation functions for the elements completely define the behavior of the field variable within the elements. For the finite element representation, in fact, of a problem, the nodal values of the field variables becomes the unknowns. Once these unknowns are found, the interpolation functions define the field variables throughout the assemblage of the elements. We would see what is assemblage. Often interpolation functions are chosen so that the field variables of its derivatives are continuous across the adjoining element boundaries. The important feature of finite element method therefore is the ability to formulate problems for individual elements and putting them together represent the entire problem. So, we start with a small problem in a region, and then one can extend the process for the whole, and that is how we can get solution for all the nodal and elemental unknown values. In fact, in finite element method, basically there are three approaches to formulate the problem, any problem, or the properties of the individual elements. One, which we call it as the direct approach, it uses direct stiffness methods of structural analysis. It can be used for relatively simple problems, and it requires the knowledge of matrix algebra in dealing with the finite element equations, and it is very easy, rather it is the easiest to understand, the direct approach. Second method, we call it as the variational approach, where it relies on the calculus of variations and involves extremizing a functional. For problem in solid mechanics, that is the plasticity problems in manufacturing, the functional terms, whatever functionality is there, it turns out to be the potential energy, the complementary energy, or some variant of these, such as the Regener variational principle. Like the variational approach can be employed for both simple problem and sophisticated element shape as well, that is to a wide variety of engineering problems. So, variational approaches are popular. Third one that comes into is weighted residual approach. It is even more versatile approach to deriving element properties. This approach begins with the governing equations of the problem and proceeds without relying on a variational statement. Using this finite element method, one can which can be extended to problems where no functional is available, and it is widely used in heat transfer problem, that is in manufacturing, heat transfer, temperature distribution of tool, etc., like this, and even it is very popular with fluid mechanics applications. So, these three basic methods are very popular. Now, let us look into the basic finite element solution, the basic steps. One can propose a very simplified manner in the 3-step process, or let us see, one can even propose the 7-step process. So, if I say the steps, the basic steps that involves finite element solution, very first step is to discretize the continuum. So, whatever continuum, it may be a 1D continuum, it may be a 2D continuum, it may be a 3D continuum. So, discretization means the whole domain of the continuum, the number and type of elements in a given problem is also very important, and its selection requires engineering judgment and experience therefore. So, once you decide that how many nodes should be there, how many elements should be there, so that is also a very important issue, and that is how you are going to discretize the whole domain into nodes and elements. And the engineering, the type of the functional in between, if it is. The second step, once it is discretized, keeping in mind with certain rules that we would be discussing later, the second step is to select the interpolation functions between these nodes, that is for the that means finding out the interpolator function. The step is to assign nodes to each element and then choose the interpolation function to represent the variation of the field variable over the element. The degree of the polynomial chosen depends on the number of nodes assigned to the element, the nature and number of unknowns. At each node, certain continuity requirements are imposed at the nodes and along the element boundaries. The third step is to find the element properties. Once the elements and their interpolation functions have been selected, the properties of the individual element, that is the matrix equation, can be determined by one of the three approaches, that is either by as said the direct approach or the variational approach or the weighted residual approach. So, the fourth step is then important enough, where you apply this to whole domain and assemble it. So, that means the fourth step is assemble the element properties to obtain the system equations. One combines the matrix equation expressing the behavior of the individual elements and form the matrix equations expressing the behavior of the entire system. So, that is how it is called as assembly. The basis for the assembly procedure starts from the fact that at a node where elements are interconnected, the values of the field variable is the same for each element sharing the node. So, if this is one element, so this node and this node. So, this value, that is the field variable is same for each element which are shared by the nodes. So, if there may be one element here, so this is the sharing node, two elements. So, field variable has to be same. The fifth step is to impose the boundary conditions. At this stage, we impose known nodal values of the dependent variable or nodal load, and accordingly the system equations get modified to get for solution. One can go ahead. And the sixth one, where then we proceed for solving. So, once you have established the assembly and then you have imposed the boundary condition, then let that now you have whole set of equations and you can solve the system equations. So, the assembly process gives a set of simultaneous equations that we solve to obtain an unknown nodal variable of the problems values, nodal values in fact. If the problem describe steady or equilibrium behavior, then we must solve a set of linear or non-linear algebraic equations. If the problem is unsteady, the nodal unknowns are a function of time therefore, and we must solve a set of linear or non-linear ordinary differential equations. And at the end, once we solve, we get the results. And then the seventh step is that you make additional computations if desired, that we call as the post processing. These results has to be whatever results have been obtained. So, one can further calculate other additional computations for other desired solutions. So, to obtain and other values that can be used for calculating other important parameters. So, this is what is the very basic 7-step method, and This is valid for all kind of problem, whether it is metal forming, whether it is a fluid related problem, or heat transfer problem, or the mix problems. There could be situation where forming is there, hot forming. So there is mixed formulation as well. So with this basic and the basic step, as I told you, these 7 steps can also be in brief, one can squeeze it in 3-step process. The 3-step means first is the pre-processing, where you create the nodes and discretization and all those things, and select the type of nodes and the variational and the functional, etc., all that. Then the solver, where you solve these matrices and all those things. And the third is the post processor, where you get the solution. And this solution, because it is nodal and element wise, so you can show it on graph with colorful map, and that's the more thing you have to calculate, so that you can show beautifully on a graph that gives some meaning, So here this slide shows some of the applications for your information, where for different situation the finite element method has been used. If you look at the first one, this is the forging problem, where so you look at there is a kind of a forging workpiece where it is to be forged. Probably it's a it can be either closed die forging or hot die forging. So if you look, the very colorful, it's a post process, that means the thing has been pre-processed, solved, and the result is shown in a very colorful manner. So that's the second one. Is the crash simulation. So there are automobiles, when it is a strike from some object, so the chances to crashing of the vehicle occurs. So one can also model, and one can know where the crash has occurred. So what has been the speed, what are the stresses at the moment of the crash, and one can design the material, proper material on the basis of this simulation, crash simulation, so that you can avoid crash. The third one is shown for the machining, where you can use the finite element method for machining, variety of machining, either it is a single point cutting tool machining, or multi-point machining, or milling operation, drilling operation, lathe operation, all kind of machining problems can also be solved. And one can use a proper tool design as well as for optimized machining. So this is what is being used today. The another figure shows for the composites. See, the composites, when composite consists of 2 basic elements as the matrix and fiber. So when both together the matrix and the fibers are clubbed, and if some load comes, then how this matrix, this composite going to behave, and that means how the stresses are going to develop, whether it is able to take loads, whether it is going to fail with a higher load. So one can simulate this process with finite element method, for either it is a single matrix or multi-matrix situation. A variety of problems are solved for matrix, including metal matrix, including resin based matrix, fiberglass, and polymer, your epoxy based matrix, like that. The other one where the finite element method is used very popularly for the material failure analysis, because one has to avoid failure, and even in metal forming, you have to form the situation with meeting a proper productivity, but avoiding any kind of failure, and particularly we call it this in a term like defect free product. So, you deform maximum with high speed, but it should not occur the failure of the material or any damage to the material. So, these material failure analyses are very well carried out with different formulation of finite element method. It may have a multi-physics problem as well, when there is the metallurgy is also consisting, forming is also consisting, heat and heat is also concerning. So, that becomes important. Another one is shown here, the crack propagation. How a crack propagates with a load, one can model with finite element method a transient problem one can take. Say there are certain crack that takes time to come at the surface and break the material or fail the material. So, how a crack propagation, crack first initiate, then it propagates and then it becomes wider to fail the material. So, these simulations are also carried out with finite element method, very popular. So, let us see if I can show you that the finite element method in 2 minutes, I can show it like this. You see, look at this slide. So, if you recall back, basically what we are doing, we are solving partial differential equations, that is the part of mechanics. So, in finite element method, almost all there is some partial differential equation which governs the physics of the problem, and then there are certain external forces. Because of the external forces, there are internal forces in balance. Then there are stresses, there are stress model like plasticity equations, the relation between stress and strain, with effect of the strain rate, it may be temperature, and then there are equations for displacement, and the displacement can be any function then. So, if you look at this, so this is what is a model, and it's a computer model as a solid model. So, basically if you look at starting with the wireframe model, which is shown as wire, and then same has been filled with, so that is called as a solid model. So, what kind of formulation is required with this? So, as you recall, the first step has been discretization. So, if you look at the second part of the same figure is shown discretizing. So, initially the number of 1, 2, 3, 4, 5 element has been chosen, 3D elements in fact. Then it was further refined to give it as a 10 elements, you can see, more than 10 elements, and then further. So, this is what is called as discretizing, and there is a method depending on the problem. The discretizing means how many elements, nodes and how many elements are, that is a very primitive, the pre-processing, we call it as all pre-processing. So, the simple answer to these could be that you first divide the whole structure into its element as shown here with simple deformation. It can be a linear element, it can be a quadratic element, it can be a other element, and let us search for the best solution. Let us, if one can find out the stresses developed at a node, stresses developed at an element. So, that is how the first thing is that you divide the whole thing into mesh. So, and that means a mesh will have corner as nodes. So one can see here there are so many nodes here. Then one has to derivation of the basic finite element equations are to be done from the partial differential equation. So this method is start to discretize the partial differential equation. So partial differential equation, that one can discretize it like here. That means if the partial differential equation for the stress is say deva sigma x bar, deva x bar plus f bar x bar is equal to 0, if this is one of the equation, so one can then multiply with virtual displacement, that is delta Vx, and that is what we call as the D'Alembert's principle. And then once you apply both sides, so the equation becomes as shown here, and then after one can integrate. So if you integrate over the volume, that is the whole continuum. So if you integrate it and then you form the weak formulation, this is what we call as the weak form of the equation. That means the partial differential equation multiplied with the virtual displacement using D'Alembert's principle and then integrate. So this is what is called as the weak form of the equation. And then this delta V, that is displacement, virtual displacement delta V bar, then tests the function if the equation is fulfilled or not. So tests are carried out, and then derivation of the basic finite element method is done. So you integrate over the volume and solve for the displacement, that is the real displacement, that is u bar, and therefore one can get, that is the sigma x bar is equal to sigma the strain, and that is one can find out the sigma deva u bar x and deva x bar, and then after that the partial integration one can perform using chain rule by this equation which is shown here, integral a to b f g 1. So that is what is the partial differential integration. So if you apply and if you include the surface traction, that is T x, T bar x, so the partial strain, that is the delta sigma V bar x deva x bar, that is the partial strain, that is the derivative of virtual displacement, and then one can find out, and this is what is shown here, that becomes the basic finite element equation. So that's the integral, that means the integral over the surface and over the volume, and on the other right side the whole domain volume, and then one can then the others step, the 7-step procedure just now I told, one can then follow it for getting the values, and then you apply it for the each node and then the assemble it, the whole thing, and then find out the equations. In fact, these integrals are converted into matrix later. So once this you have the matrix, these matrix would be solved after once the assembly is done, and then you apply the boundary condition to that. Once you apply the boundary condition, you find out the unknown variables over the that is the field variables, unknown field variables, and then that is what is the where you follow some numerical method for solving the matrix manipulation, and then the stabilizing, then the accuracy checking of the equations, then the convergence criteria, and with certain accuracy the repeating of the whole process, and then converge, check it again. So iterative process is followed unless you get a a proper result which is restricted within a given accuracy level. So these basic equations along with the boundary conditions are solved and one can then get a solution. We would continue this lecture in the next lecture as well, because there are further some few more things are to be discussed. So we would continue this lecture in the next one, but I hope you will practice the basic whatever procedure of finite element method is we discussed today. You will revise and will see it again tomorrow, but please look into these aspects, like what are the advantages, what are the disadvantages of finite element. I have already told, but one has to revise it, so that is very basic things to keep in mind. So while establishing this formulation, we may start with 1D problem, then let us initially start with this 2D problem and let us solve first with the stress strain problem. So we would go ahead with some real life problem of forging or something like that, so that one may have the flavor of metal forming where the finite element method is used as modeling technique. So with this hope, I take a break here, and with the hope that we would be meeting in the next lecture, and I will thank you for your patience, with the request that you please revise it, and if the objective problems are available at the net, you please solve it, check your understanding, and also give your feedback to us, so that we can improve if there is any lagging on our side. So thank you very much. Thank you.